Hi, this is Mohammad Rakibul Hassan presenting our paper An Evolutionary-based Neural Network for Distinguishing Between Genuine and Posed Anger Videos from Observers Pupillary Responses. So these are the outlines of my presentation. First, I'll be talking about introduction or the motivation behind this work. Then I'll be talking about specific methods that we utilized in this particular work. Then what are our outcomes, what we achieved so far as results, and then I will be comparing with two methods that we utilized. One is the backpropagation optimizing and another is evolutionary algorithm optimizing, and also I will be talking about comparison with recent literature based on similar work, and then I'll be talking about conclusions with possible future works. So let's dive into the presentation. Let's start by introduction. So first of all, what is the motivation behind this particular work? So as we know that computing is being more and more ubiquitous. So we have different smart wearables like different sport watches, different health monitoring tools, smartphones, and so on. So who are their primary users? Of course, it's us humans, and we have emotions. But the thing is that these emotions can be acted. Now, how to uncover whether this is an acted emotion or this is a real emotion? So this is the particular questions we want to identify, we want to answer in this particular work. Now, this particular research by Quinn and others, they showed that people are generally poor at distinguishing genuine and acted anger, having an accuracy only around 65%. So, question is, can they unconsciously recognize acted versus real anger? So this is the specific question we want to answer in this work. So to answer this particular question, instead of using volunteer subjective judgment, that means volunteer won't say that this is real or this is posed. Rather, we will use their pupillary responses. So, of course, I must say this is not a brand new idea. Now, what are our improvement? So, first of all, we intend to find out the simplest possible model along with preserving a reasonable performance score. And also, we further prune our developed model, and we did it in a systematic way, not a random manner. So we removed redundant neurons in this pruning process, and also we utilized evolutionary algorithm training. So let's talk about the methods we employed. So first of all, this is the overall flow chart that we followed in our work. Basically, the dataset composed of pupillary responses. So the dataset is made by using several volunteers. So they basically observe genuine and posed anger videos, and their pupillary responses are collected. So we extract several features from that pupillary response, and then we use those features in neural network classifier, and we train that particular classifier in two ways. One is evolutionary algorithm optimization and also in the backprop optimization. So then of course we got our trained network, and further we prune that trained network in a systematic way, and finally we got our trained neural network and other similar analysis. So regarding the data set, basically Sen and others, they reported the pupillary responses of 20 volunteers while they were watching 20 videos, and among those 20 videos there were 10 genuine anger and 10 posed anger. Now what are the sources? Of course YouTube, the great source of videos. Now one might ask, what are the ground truths? I mean, how this genuine and how this posed anger are identified as ground truth. So the genuine video sources are basically documentaries and news, since we know that in documentaries and news the anger, if shown, then of course that will be real. Whereas in film, of course film are acted, so that's why the posed videos were treated as movie clips of not famous actor. Now the thing is, why not famous actor? Because we want to reduce any bias. So if those if those videos of famous actor, then of course the observers will know that it is acted anger, since we all know that in movies they are all acted. So that's why those movie clips are not from any famous actor. And also other similar thing like those videos were for same resolution, so that potentially any biases they don't appear. And regarding the features, so we extracted these 6 features and dimensions. So mean and STD basically refers to the mean value and standard deviations of observers' pupillary responses. diff1 and diff2 basically refers to the change of observers' left and right pupil size respectively, and PCAD1, PCAD2 refers to the orthogonal linear transformation with the first and second principal component. Now if we inspect the data, so these are basically density plot of all those 6 features. Now if we look closely, except this first one, PCAD1, for all those 5 different features there are no considerable differences in this density plot. So they look like same in terms of this density plot. So of course we can say that in the classification of anger and post real and post anger videos, they will not contribute as much as PCAD1 will contribute. So since PCAD1 has shown differences, so we can conclude that this particular feature will conclude more in the classification. Now in the data pre-processing step, of course it is well known that suitable data processing can improve the performance of data-driven models. So specifically we utilize this particular data processing technique. So what we did here, X refers to the unprocessed data. So we subtracted those unprocessed data by its mean, and then we divided by the standard deviation, and this particular operation is being done on all those 6 dimensions, and by this process we obtain the pre-processed data. Now what are the benefits of we found in this particular work? So of course we found speeding up in the training process. So without pre-processing it took around 20,000 epochs, whereas with pre-processing it took around 5,000 epochs only. And these two comparison, basically it is on the same NN model optimizer and loss function. So of course we found around 4 times speed improvement here. Now the configuration of our basic neural network model, so we had 2 hidden layers. So we have the first input layer, and as we said that we have 6 features, so it has 6 neurons, and then in our first hidden layers we have 6 neurons, and also in our second hidden layer we have 6 neurons. And since we are talking about a binary classification problem to classify real and post anger, so at the output we have 1 neurons. And in terms of activation function, so in the first 2 hidden layers, first and second hidden layers, we have ReLU activation function, and since it is a binary classification problem, so of course in the last layer we have the sigmoid activation function, and we used binary cross entropy as the loss function and stochastic gradient descent as our target optimizer to train the model. Let's talk about evolutionary algorithm on optimizing NN. So first, to code the individuals in our population, so here individual means it is basically those weights and biases. So this is well known that the number of weights and biases in a model can be referred by this particular equation. So it is related to the number of neurons. So if we calculate the number of weights, so as we know that in our input we have 6 neurons, and in our first hidden layer we have 6 neurons. So at first we have 6 into 6, this one, and similarly as we are saying that in our first hidden layer we have 6 neurons, and second hidden layer is also 6, so 6 into 6 biases. And lastly we have 1 in the output layer, and in the second hidden layer we have the 6 neurons, so 6 into 1 at the end. So we have 78 weights here, since this is a fully connected network. And in terms of biases, So we have 6 plus 6 plus 1, that means 13 bias parameters. So in total we have 91 weights and biases. So this is the length of an individual in our population. And to evaluate these individuals, we used evaluate accuracy method as the fitness function. Our target is to maximize the fitness function. Now in the population initialization, what we did, we initialized those weights and biases by random numbers. So of course 91 real numbers having standard normal distribution. And in the selection process, we used tournament selection algorithm where our turn size parameter was 3. That means every time we randomly pick 3 individuals and choose the individual with the best fitness to the pool of offspring. And this finding the offspring was repeated until the required number of individuals has been selected. And in the crossover, we used blend crossover algorithm to realize gene transfer. And specifically for mutation, with an independent probability, there was like every gene sends to a random number according to Gaussian distribution, and we set the variance of Gaussian distribution as 0.1, and the independent probability was set to 0.4 there. And this is our general setting to optimize using evolutionary algorithm. So we initialize the population as 100 individuals. Our crossover probability was 0.8, having a mutation probability of 0.4, and we ran the algorithm for 800 generations. Now regarding the pruning on hidden layer, or we can say the compression on hidden layer, so our question here was to do the hidden layer of the network have any redundancies? To answer this question, we use this distinctive analysis. So first we used activation matrix. So we calculated the activation matrix, which is basically the output matrix of a particular layer, and we focused on second hidden layer for this particular compression technique. So in that activation matrix, the columns corresponds to on hidden units output. So since they are on hidden units output, so we analyze the similarities, specifically cosine similarities between those columns. So this is the distinctiveness of hidden unit. So if that similarity is high, in those cases we deleted any of them. Specifically we deleted the first one of the most similar to hidden units and added its weights and bias to the second unit. So this is our pruning process that we did on the second hidden layer. Now let's talk about results. So first we started with neural network configuration and its possible basic optimization. So these two figures are for not pre-processed data. So at first we had used learning rate of 0.05 with a momentum of 0.8, and when you used a railway activation function, so our maximum accuracy was around 55%. But at first when we changed this activation function to 10s, if we notice, and it was flattened at around 60%. So of course this is an improvement from ReLU to 10s. Now later when we worked with pre-processed data and when we changed the learning rate, so when our learning rate was around 0.001, so our maximum accuracy was roughly around 75%. Now when we increased that learning rate to around 0.017, now if we notice, the accuracy, the highest accuracy was around 85%. So this is the best possible result so far we achieved using backpropagation optimization. Now in case of evolutionary algorithm, after 800 generations of evolution, we achieved 86% accuracy. So our maximum accuracy was 86% in evolution algorithm training. And regarding the result of neural network pruning, so what we did, we ran for first 10,000 epochs backpropagation training without any pruning, and then we did the distinctive analysis. We pruned on hidden units one after another. Right after pruning on hidden unit, we ran for another 10,000, another 1,000 epoch. So this is the result. So at first when on unit pruned, we can see that the result is not decreased. The accuracy is quite high as well. even after pruning 2 units, the accuracy is still high, good. But after pruning 3rd hidden unit, we can see the performance is decreasing. And specifically, when 4th unit is pruned, then its performance is decreased significantly. So of course we can say that 2 hidden units can be deleted here without any tension, and 3rd hidden units can also be deleted from here as well. Performance is reduced slightly. And let's talk about comparison. So first of all, if we compare between backprop and EA method, so in backprop we ran for 10,000 epochs and that gave us accuracy of 85%, and in evolutionary algorithm we ran for 800 generation and that gave us 86% accuracy. Now it is well known that backprop has a problem with stacking at local minimum. So the question is, was the backprop constrained by any local minimum? Now we cannot be conclude with complete certainty, but we can say that we know that EA usually has a good performance on finding the global best solution. So therefore, as we see that the accuracy of backprop and EA are quite similar, so we can say that backprop was not constrained by any local minimum. And lastly, if we compare similar neural network based works on the same ICAART data set, then we found that our work is right after the best possible work. The best one was best accuracy so far reported by Wang and others. They found 93.6% accuracy. Now if we compare, so Wang and others, they used 2-stream neural network based model, and in each of their stream they use 60 hidden neurons. In total they had 120 hidden units in those 2 streams. And right after that 2 stream, they also used a fully connected final prediction layer. Whereas in our proposed method we used a simpler feed-forward neural single stream architecture, everyone will say, whereas we used 20 hidden units. If you remember, we have 2 hidden layers, and each layers we have 6 neurons, so we have 12 hidden units before pruning. Also we pruned it later. So even if we consider that unpruned network, of course that is around 10 times less in terms of number of hidden units. So we think that is one of the reason of performance degradation here. So our aim was to find reasonable performance with simplest model possible. Now if we talk about conclusions and future work, so regarding conclusions, so of course we developed a simple NN to classify real and post ICAART based on observed pupillary responses, and we optimized NN in 2 ways, backprop and evolutionary algorithm, and we achieved 86% accuracy using evolution algorithm, and also our backpropagation algorithm gave us 85% accuracy. And we also compared this particular score with recent literature based on the same data set, and we can say that even using this simple architecture, our score is quite competitive. And also we showed the pruning process. There we can say that 3 neurons can be removed with significant performance degradation, and 2 neurons can be removed without any performance degradation there. And of course the question we raised earlier, Observers Pupillary Response patterns could reflect the ICAART veracity even though the perceivers are unconscious. So that means unconsciously we can recognize whether an ICAART is acted or real. So regarding future works, we could use alternate models to benchmark. Several statistical tests could be employed to validate, and also we can use people's speech emotion to predict whether their facial emotion is genuine or not, which could be interesting, we believe. And also advanced network pruning techniques such as using threshold or structured filter level pruning could be employed. And let's talk about reference cited in this presentation. So these are the references that are cited in this particular presentations. So with that, I'd like to end here. Thank you everyone for hearing me. So floor is now open for discussion.